Welcome to the deep dive. Today, we're really plunging into the world of machine learning algorithms. It can seem pretty complex, right?
Oh, absolutely. Lots
Yeah.
of jargon flying around.
Exactly. So our mission today is to cut through that noise, skip the heavy textbook stuff, and give you a real shortcut to understanding the core tools that power modern AI,
Yeah, what they actually do.
right? And where you might actually bump into them, maybe without even knowing it.
And understanding these building blocks is just key because they're not just theory, they're really shaping our digital lives every day.
hmm
The sources we've got lined up, they're kind of like a cheat sheet, really. A great overview if you're curious.
Perfect. And we've structured this sort of like a journey. We'll start with algorithms that learn from examples.
Like being taught.
Yeah, exactly.
Right.
Then we'll look at ones that have to find patterns all on their own. After that, simplifying really messy, complex data.
Always useful.
And finally, we'll get into those brain-inspired models that are behind a lot of the really cutting-edge AI stuff. So, yeah, let's unpack this the foundation, supervised learning, learning from examples. Okay, let's kick things off with supervised learning. The way I think about it, it's like training a kid with flashcards. You show it something, tell it the right answer.
And it learns the pattern.
Yeah, it figures out the rules over time.
That's spot on. The supervision is literally that labeled data. You have an input and you know the correct output that goes with it. That guides the whole learning process.
Okay, so let's say we want to predict a number, like, I don't know, next quarter sales or maybe a house price. Where do we usually start? What's the foundational algorithm there?
Right. For predicting those continuous values, linear regression is usually your first port of call. It's fundamental statistics, really.
Okay.
The core logic is trying to find the best fit line or, a flat plane if you have more inputs, a hyperplane that describes the relationship.
So like drawing a straight line through a bunch of data points on a graph.
Exactly. It finds the coefficients, the numbers in the equation, y equals b0 plus b1x plus a to add that make that line fit the data as closely as possible. Simple, usually easy to understand.
Makes sense. So it's great for something like house price prediction. You feed it square footage, number of bedrooms.
And it spits out a price estimate, yeah.
Huh.
Its simplicity and interpretability are big pluses.
But there's always a but, right?
Well, yeah. It assumes a linear relationship. If your data actually follows a curve, a straight line just won't cut it. And it can be quite sensitive to outliers, those really unusual data points.
Gotcha. So not great for wiggly data. What if we're not predicting a number, but deciding between categories? Like, is this email spam or not spam?
Ah, okay. So for that, surprisingly, you often use logistic regression.
Wait, regression? I thought you said that was for numbers.
I know, the name is super confusing. It's actually for classification, usually binary, 2 categories. Yes, no, spam, not spam, that sort of thing.
Huh. Okay, how does that work then?
It starts with that same linear equation, but then it does something clever. It passes the result through a special function, the sigmoid function.
Sigmoid.
Yeah, think of it like a squashing function. It takes any number, big or small, positive or negative, and squeezes it into a value between 0 and 1.
Ah, like a probability.
Exactly. So it outputs the probability of belonging to one class. For spam detection, maybe an email gets a 0.9 score. If that's above our threshold, say 0.5, boom, classified as spam.
Okay, so it gives you a likelihood.
Yeah.
That's useful, still pretty interpretable.
Yeah, generally. But again, it's basically drawing a line, albeit a squashed one. If the boundary between your classes is really complex and curvy, logistic regression might struggle.
Right. Okay, moving on. Have you ever done one of those flowcharts, like for diagnosing a problem? If this, then that.
Oh, yeah, definitely.
Well, that's kind of how a decision tree works, isn't it?
Yeah.
It mimics that step-by-step decision process, and you can use it for both predicting numbers and classifying.
That's a great way to put it. It works by making what's called a recursive binary split. At each point, each node, it asks a simple question about one feature.
Like, is income over $50?
Precisely. Or, is age under 30? And based on the answer, you go down one branch or the other, asking more questions until you land on a final prediction or classification.
And the big win here is you can actually see the path it took, right?
Absolutely. That's its superpower. Interpretability. It's a white box model. You can literally trace the logic. That's why banks might use it for loan default prediction. They can explain why a loan was approved or denied based on the tree's rules.
But I remember hearing they can be a bit unstable.
That's the main drawback. They are very prone to overfitting. They can learn the training data, including all its noise and specific quirks, too well.
Meaning they don't work so well on new data they haven't seen.
Exactly. A single tree can be quite sensitive to small changes in the data, leading to a completely different structure, not always reliable on its own.
Okay, so one tree might overthink things. But what if we could combine, like, a whole bunch of trees? Does that help?
Now you're thinking like an ensemble method.
Got
Yes,
it.
combining multiple models, especially trees, is incredibly powerful. This is where it gets really interesting.
Put it on me.
Okay, first step, the random forest. Imagine, instead of asking one expert, you ask hundreds, each with slightly different background knowledge.
Okay.
A random forest builds a whole forest of individual decision trees. But here's the trick. Each tree is trained on a random subset of the data points, and it only considers a random subset of the features at each split point. That's called bagging.
So each tree is slightly different, sees things a bit differently.
Exactly. Then, to make a final prediction, the random forest either averages the results for regression or takes a majority vote for classification from all the trees in the forest.
And the collective wisdom smooths out the errors.
Precisely. It dramatically improves accuracy and makes the model much more robust. It combats that overfitting problem we saw with single trees. That's why it's great for fraud detection, analyzing lots of transaction data reliably.
Sounds pretty powerful. Downside.
Well, it's slower because you're building many trees, and you lose some of that nice interpretability of a single tree. It's harder to see exactly why the forest made a certain decision, so maybe not ideal if you need results instantly.
Okay, voting trees. Got it. You mentioned another ensemble method, gradient boosting. How's that different?
Gradient boosting. Also very powerful, but takes a different approach. Instead of building trees independently and voting, it builds them sequentially.
Sequentially, like one after the other.
Yeah. The first tree makes a prediction. The second tree is then built specifically to correct the errors the first tree made. The third tree corrects the errors of the first two combined, and so on.
So each new tree is focusing on the mistakes of the team.
Exactly. It's iteratively minimizing a loss function, basically, trying to get better and better at reducing the overall error with each new tree it adds. This often leads to, well, state-of-the-art results, especially on tabular structured data.
Wow. Okay, so for something like credit scoring, where you need maximum accuracy.
It's a very strong contender, definitely.
Sure.
The predictive power can be incredible.
Yeah, gotta be a catch.
Again, complexity and interpretability. It can be even more prone to overfitting than random forest if you don't tune it carefully. And it's very much a black box. Getting a super accurate score is great, but explaining why someone got that score can be really tough. Not ideal if explainability is legally required, for instance.
Right, the black box problem. Okay, let's quickly hit a few other big names in supervised learning. Support vector machine, SVM. Sounds technical.
It is a bit, but the core idea is cool. For classification, SVM tries to find the best line, or hyperplane, to separate the classes, but it specifically looks for the one that creates the largest possible margin or street between the classes.
A wider gap is better.
Yeah, the idea is that a wider margin makes the classification more robust, and for data that can't be separated by a straight line.
Which is most real-world data.
Right. It uses something called the kernel trick. It's like, imagine projecting your data into a higher dimension, where suddenly a simple line can separate the classes cleanly. It's a clever mathematical move.
Okay, kind of mapping it to a space where it's easier to divide. Why is that useful?
It's really effective in high-dimensional spaces, like when you have tons of features. Think facial recognition, dealing with thousands of pixel values. SVMs can handle that well and are relatively memory efficient.
Downside.
They can get quite slow on very large data sets, and if your classes overlap a lot or the data is very noisy, finding that perfect wide margin can be difficult or impossible.
Okay, next up, KNN, K-nearest neighbors. You call this one lazy.
Yeah. It's often called a lazy learner because it doesn't really do much learning up front.
How does it work then?
It's super simple, actually. To classify a new data point, it just looks at the K data points from your training set that are closest to its nearest neighbors.
K being a number you choose, like 3 or 5 neighbors.
Exactly. Then it just assigns the new point to whatever class is most common among those K neighbors. Majority vote wins. Simple. No real training phase needed.
I can see that being used in recommender systems, right? Like, people similar to you also like this movie.
That's a perfect analogy. It finds your neighbors based on viewing habits and recommends what they liked.
But lazy sounds slow.
It can be for predictions, because for every new point, it has to calculate the distance to all the existing points to find the neighbors. That gets slow with lots of data, and it doesn't handle high-dimensional data very well. The recursive dimensionality makes distances less meaningful. Noise can also throw it off easily.
Right, distances get weird in many dimensions.
Yeah.
Okay, last one for this section. Naive Bayes. Sounds naive.
It is intentionally so. It's a probabilistic classifier based on Bayes' theorem from statistics. Its naive part is a big simplifying assumption. It assumes that all the input features are completely independent of each other.
Independent. Like one feature doesn't affect another at all.
Exactly. Which in reality is often not true, especially in language where words influence each other. But
It works anyway.
surprisingly often, yeah.
Yeah.
Especially for text classification, its big advantages are that it's incredibly fast and works well even with lots of features, like words in a document.
Ah, so sentiment analysis, figuring out if a review is positive or negative based on words, that's a good fit.
Perfect fit. It can quickly tally up probabilities based on word occurrences, but if the interaction between features is really important for the problem, that naive assumption will cause it to fail. 2. Uncovering hidden patterns. Unsupervised learning, no labels needed.
Okay, deep breath. We've covered learning with labels. Now let's switch gears entirely. What if you just have data, loads of it, but no labels, no right answers provided?
Right, this is the realm of unsupervised learning. The algorithm has to figure things out for itself, find structure or patterns hidden within the data.
Like grouping similar customers together without knowing beforehand what the group should be.
Exactly. It's about discovery. Discovering inherent structures, clusters, relationships without any prior guidance, finding the story the data tells on its own.
And the big name here is K-means, right? The most common clustering algorithm.
Definitely one of the most popular. Its goal is to partition your data into a pre-specified number, K, of clusters.
K again. So you have to tell it how many groups to find.
You do, that's one of its constraints.
Yep.
It works iteratively. It randomly picks K starting points, called centroids. Then it assigns every data point to its nearest centroid. Then it recalculates the centroid to be the average of all points assigned to it.
And it keeps doing that. Assign, recalculate, assign, recalculate.
And until the centroids stop moving much, meaning the clusters are stable, it's pretty fast and easy to implement.
Makes sense for customer segmentation. Grouping customers based on purchasing habits or demographics for targeted marketing.
Classic use case. But besides needing to know K beforehand, it also assumes clusters are roughly spherical and evenly sized. It struggles with weird shapes or clusters of different densities.
Okay, so K-means likes nice round blobs. What if the structure is more complex, maybe nested?
Then you might look at hierarchical clustering. This approach builds, well, a hierarchy of clusters.
A hierarchy, like a tree.
Exactly. It creates a tree-like diagram called a dendrogram. This shows you how individual points merge into small clusters, and those small clusters merge into bigger ones, and so on, all the way up.
Oh, cool. So you can see the structure at different levels.
Right. And a big advantage is you don't have to specify the number of clusters K beforehand. You can look at the dendrogram and decide where to cut the tree to get the number of clusters that make sense. It gives you a much richer view.
I see that being useful in biology, like gene expression analysis, seeing how groups of genes relate to each other.
It's definitely used there. The major downside, though, is that it's computationally heavy. Calculating all those pairwise distances and building the tree gets really slow and memory-intensive for large data sets. Impractical for, say, tens of thousands of points or more.
Got it. So not for massive data. What else is there for clustering? DBS-CAN. Sounds like some kind of scanner.
It's density-based. DBS-CAN stands for Density-Based Spatial Clustering of Applications with Noise.
Catchy. How does it work?
It defines clusters differently. Instead of relying on a center point like K-means, it looks for dense regions of points. A cluster is basically a bunch of points packed closely together, separated from other clusters by sparser areas.
So it finds dense patches.
Yeah. And importantly, it can identify points that don't belong to any dense region. It labels them as outliers or noise. This is a big plus. It can also find clusters of arbitrary shapes, not just spheres.
Oh, it's useful. So for geospatial clustering, like finding hotspots of activity on a map, it could find weirdly shaped, dense areas.
Exactly. It's great for that. It doesn't care if the cluster is shaped like a circle or a banana. Its weakness, though, is that it struggles if your clusters have very different densities. It might merge a sparse cluster into a dense one or miss the sparse one altogether, and it doesn't always work well on very high-dimensional data.
Okay, density is key.
Huh.
Now, one more in this unsupervised space. Autoencoders. You mentioned these are neural networks.
They are, but used in an unsupervised way for representation learning. It's a really neat idea.
Go on.
An autoencoder has two main parts. An encoder network takes your input data and compresses it down into a much smaller, dense representation, a sort of bottleneck, often called the latent space.
Squeezing the information down.
Right. Then a second network, the decoder, takes that compressed representation and tries to reconstruct the original input data as accurately as possible.
Okay, so it compresses then decompresses. What's the point?
It's trained to minimize the difference between the original input and the reconstructed output, the reconstruction loss. If it can learn to reconstruct the data well after squeezing it through that bottleneck, it means the compressed representation must have captured the most important features.
Ah, so it learns a useful, compressed version of the data. For what?
Great for data compression, obviously, but also really good for anomaly detection or fraud detection. You train it on tons of normal data. Then, when you feed it an unusual or fraudulent data point,
It won't know how to reconstruct it properly.
exactly, it will have a high reconstruction error because the weird input doesn't fit the patterns it learned from the normal data. That high error flags it as an anomaly. They can also be good for denoising images.
Clever. Downsides.
They can overfit if that middle compressed layer isn't small enough. And like other neural networks, they can be black boxes. Plus, if you don't actually need compression or anomaly detection, they might be unnecessary overhead.
3. The art of simplification. Dimensionality reduction. Okay, so we've seen learning with labels and finding patterns without them. But sometimes the problem isn't the labels, it's just too much data, too many features.
Definitely. Having hundreds or thousands of features can make models slow, hard to train, and sometimes the extra features just add noise and confuse things. This is where dimensionality reduction comes in handy.
The art of simplification, as you called it earlier.
Pretty much. The goal is to reduce the number of features, the dimensions, while losing as little important information as possible, like writing a concise summary of a long book.
And the main technique here is PCA, Principal Component Analysis.
That's the classic one. PCA isn't really for prediction itself, it's more for pre-processing, for simplifying your data before feeding it into another algorithm.
How does it simplify?
It looks at your data and tries to find new axes, new directions called principal components that capture the maximum amount of variance or spread in the data.
Variance meaning how much the data points differ.
Yeah, essentially where the most action is happening in the data. The first principal component captures the most variance, the second captures the next most, and is uncorrelated with the first, and so on.
So you can keep just the first few components.
Exactly. You might find that, say, the first 10 principal components capture 95% of the variance in your original 100 features. So you can just keep those 10, drastically reducing dimensionality. This helps reduce noise and speeds up subsequent training.
I can see image compression being a good example, representing an image with fewer components instead of every single pixel.
Perfect example. You can get significant compression with minimal visible quality loss.
What's the catch with PCA?
The main one is interpretability. These new principal components are mathematical combinations of your original features. They don't usually correspond directly to anything meaningful in the real world like age or income. They're just abstract directions of variance.
So you lose the meaning of the original features.
Pretty much. If you absolutely need to know how each original feature contributes, PCA might not be the right tool. And it assumes variance is the most important thing. If critical information lies in low variance patterns, PCA could miss it. 4. The brain-inspired models, neural networks and beyond.
All right, final section. Let's talk about the heavy hitters, the algorithms that really feel like AI, the brain-inspired models. These can learn incredibly complex stuff, right?
They really can. This is where a lot of the excitement in AI has been focused for the last decade or so. These models form the backbone of many modern AI applications.
Starting with the basic concept, neural networks, maybe specifically the MLP, the multi-layer perceptron.
Right. The MLP is a foundational type. Think of it as layers of interconnected neurons. Each connection has a weight, and each neuron sums up its weighted inputs and then applies a nonlinear activation function before passing the result to the next layer.
Layers upon layers.
Yeah.
Doing math.
Sort of. That layered structure with the nonlinear activations allows them to learn very complex hierarchical patterns. Lower layers might learn simple features like edges in an image, and higher layers combine those to recognize more complex shapes or objects. Their power lies in that nonlinear learning.
And the classic example is image classification, telling cats from dogs.
That's a core application. They can learn the intricate patterns needed to distinguish between many different object classes.
But they need a lot of data, right? and computing power.
Absolutely. They are data hungry, often requiring massive data sets to train effectively. They're also computationally intensive, needing powerful hardware like GPUs, and they're often black boxes, very hard to interpret why they made a specific classification. For simple problems, they can be total overkill.
Okay, so that's the basic idea. But then things got more specialized, like CNNs, convolutional neural networks.
Exactly. CNNs were a major breakthrough, specifically designed for grid-like data, especially images.
What's special about them?
They use special layers. Convolution layers act like feature detectors, sliding filters over the image to find patterns like edges, corners, textures, regardless of where they appear. Pooling layers then downsample the information, making the network more efficient and robust to small variations.
So they're built to look for visual patterns.
Precisely. This architecture makes them incredibly effective for image tasks, achieving state-of-the-art results in classification, object detection, segmentation, you name it.
Makes sense why they'd be crucial for self-driving cars needing to identify everything on the road in real time.
Absolutely critical. Their ability to process visual information is key. The downside: even more data hungry and computationally demanding than basic MLP is often requiring specialized hardware, GPUs, for training and even inference, and they're really only suited for that grid-like data structure.
Okay, so CNNs for grids like images? What about sequences like text or time series data?
For that, we have RNNs, recurrent neural networks. They are designed specifically for data where the order matters.
How do they handle order?
They have a kind of memory. They use feedback loops, allowing information from previous steps in the sequence to persist and influence the processing of the current step. This internal state lets them capture dependencies over time or through a sequence.
So they remember what came before. Useful for stock prediction, using past price movements.
Yes, or understanding sentences in natural language or processing speech signals. Anywhere, sequence context is important.
Seems powerful. Any limitations?
The main one for basic RNNs is the vanishing gradient problem. It becomes very difficult for them to learn dependencies over very long sequences. The signal from far back in the past tends to fade out, making it hard to connect distant events.
So long-term memory is tricky. Which leads us, I guess, to the real modern powerhouse, transformers, like BERT and GPT.
Exactly. Transformers really revolutionized the field, especially natural language processing, NLP. They overcame that long-range dependency problem in a very clever way.
Oh, what's their secret sauce?
The key innovation is the attention mechanism. Instead of processing the sequence step by step like an RNN, a transformer looks at the entire sequence at once. When processing a specific word, the attention mechanism weighs the importance of all other words in the sequence, no matter how far away, allowing it to draw context from anywhere.
So it can pay attention to relevant words anywhere in the text.
Precisely. Positional encoding is also added to give the model information about word order, since it's not processing sequentially. This combination allows them to capture complex relationships and nuances in language incredibly well.
And that's what's behind things like advanced translation bots or chatbots like ChatGPT.
Yes, they power most state-of-the-art NLP models today. They can understand context, generate coherent text, translate languages with amazing accuracy. It's a huge leap forward. They're also generally faster to train than RNNs because the calculations can be parallelized more easily.
Okay, but the scale, they sound enormous.
They are. That's the main con. They require absolutely massive data sets for pre-training, think huge chunks of the internet, and are extremely large models demanding significant computational resources, often multiple powerful GPUs or TPUs, both for training and even just running them. Definitely not practical for small projects or limited budgets without using pre-trained versions. Outro.
Wow. Okay, that was quite a journey through the algorithm zoo. We went from simple lines and decision trees all the way to these giant transformer models. It really gives you a sense of the toolkit available.
It really does. From learning with explicit answers to finding hidden patterns to simplifying data to mimicking complex cognitive tasks, there's an amazing diversity of tools.
And hopefully, for you listening, understanding these helps make sense of the AI buzzwords. You can start to see how things like recommendations or spam filters or even chatbots might actually work under the hood.
Yeah, these aren't just abstract ideas anymore. They're deeply embedded in the technologies we use every single day, shaping industries, changing how we work and live. It's not just theory, it's practice.
So a huge thanks for joining us on this deep dive into the world of machine learning algorithms.
Yeah, thanks for tuning in. It does leave you with a thought, though. As these tools, especially the complex neural networks, become even more powerful and pervasive, how do we make sure we understand what they're doing, especially when they operate like black boxes? Maintaining interpretability and control is going to be a huge challenge moving forward.